Hello and welcome everybody. In this video we're going to look at the total energy stored in a capacitor. So in the previous videos we looked at how we can derive formulas for capacitors and how we can build capacitors from parallel plates, and we also looked at the electric field produced by a capacitor with the parallel plates like this. So we have here some positive charge on one of the plates and some negative charge on the other plates, and the total charge here is plus q and here it's minus q, and we saw that there is an electric field that looks like this, more or less like this, in the capacitor going from the positive plate to the negative plate. And this describes the path that a positive charge would take. If you put a positive charge around here, it would take this path from the positive plate to the negative plate. And this is of course because the positive charge would be repelled by the positive charges on here and would be attracted by the negative charges on here. So the effective electric field in the capacitor is actually a sum of the electric fields of both plates. So it's not just one plate that is producing the electric field, it's both plates together, and the fields are in the same direction. And we also saw then that the electric field for this is a for this capacitor is a constant, and this is equal to 4 times k times pi times the sigma charge density sigma. And we also saw that the charge density is equal to the charge divided by the area of each plate, and so this is equal to 4 k pi times q over a. And notice that this is the total electric field due to both plates. The electric field due to a single plate is just half of that, so it's 2k pi q over a, and this is equal to the magnitude of the electric field divided by 2. And so okay, so now we want to look at the energy. What is the total energy stored in this capacitor, and what does that even mean? Suppose the capacitor is uncharged, so there are no charges in either of the plates, and you take a battery and you connect. So here's the capacitor and it's uncharged, and you take a battery and you connect it to the capacitor here. So this is the positive side, this is the negative side. So this battery is going to do some work in order to push the positive charges into this plate, and in accordingly to push the negative charges on this plate. And that's of course the same as taking positive charge from this plate. So you can see it as this: the battery is pushing positive charge on this plate and removing positive charges from this plate, or alternatively it's pushing negative charge into this plate and removing negative charge from this plate. So negative charge comes this way, and then negative charge comes here, it's negative. And the other way to look at it is positive charge goes here and positive charge leaves here. So what is this? So the battery, in order for the battery to separate the charges like this and to push positive charges on this plate here, it has to do some work. Initially it doesn't have to do much work because the capacitor is not charged, so there are no forces here repelling the addition of more positive charges. But as you start to increase the positive charge on here, you start to add more positive charge, it's going to get harder and harder for the battery to be able to push more positive charges on here, because these charges will repel the positive charges pushed by the battery. So the battery has to do more and more work to go against this electric field. As you can see, the electric field here is not constant. It starts to increase because the more positive charges are added. So the first thing to know is that the electric field, while the capacitor is charging, is not constant. It depends on the amount of charge on the capacitor, and accordingly it also depends on time then. So if we tried to use the formulas, we know the formula for a capacitor is the capacitance is equal to the charge divided by the voltage. If you simply try to use this formula in order to calculate the energy, you're going to make a mistake, because this formula assumes that the charge and the electric fields are constant in time. So we have to take into account the fact that the electric field here is not a constant while the capacitor is charging. It's changing, and that will change the amount of work that the battery has to do for each slice of time, and so that will give a different answer. So what is the correct answer then? In order to find this, we have to consider an infinitesimal amount of energy that is added into the capacitor by the battery, and we call this amount of energy dE. dE means the differential voltage of E. Sorry, not the differential voltage, the differential of E. And this just means a very, very small quantity, just a little bit of energy. And so we say that dE is equal to the voltage. Now this voltage is dependent on time and also dependent on the amount of charge that we'll have. In this case, it will be dependent on the amount of charge that the capacitor is holding. And just to revise, this formula may seem a bit strange, but actually, let me first write down the formula and then I'll explain where it comes from. So dE, the differential voltage, is equal to the voltage times dQ, where dQ is a very small amount of charge. So where does this come from? Remember that voltage is equal to energy. So this is energy per coulomb of charge. So energy per charge. So you take some amount of energy, you divide by the charge, and that will be equal to the voltage. So voltage is energy per charge. So if you want to calculate the energy, then energy is going to be voltage times charge. So if you multiply both sides of this equation by charge, then you get charge times voltage is equal to energy. So that's why we use this here. The differential of energy is going to be equal to the voltage times the differential of charge. And now it's in order to solve this equation, the first thing we have to do is to substitute voltage in terms of charge, because this is what we have here. This is how the capacitor works. So voltage, in order to get voltage from here, you just multiply both sides by voltage and divide both sides by C. So this voltage is equal to charge divided by capacitance, and so we just substitute this into here, and so dE is going to be equal to Q over C times dQ. Okay, so now we have a differential equation that we can solve, because the variable here dQ is the same variable that we have here, Q. In this previous case here, there's no way that we can solve this equation because V is a different variable than Q. So you have to rewrite V in terms of Q so you can solve this. And the way to solve this differential equation is to simply integrate both sides directly like this. And to integrate means to add all of the small infinitesimal values that you have to get a finite value. And so we have, if we integrate the differential of energy, we simply get energy, and this is going to be equal to, if we integrate this, we can pull the constant capacitance outside, so this is 1 over C. And to integrate Q, this is a simple polynomial integration. So if you have the integral, for example, of x to the nth power dx, now x is the variable and n is just a constant, it's just a power. It could be, for example, x squared or x cubed, x to the 0, which is equal to 1, and so on. So in order to integrate this, the result is going to be equal to simply x to the n plus 1 divided by n plus 1. You just add 1 to the power and divide by the same number. This is going to be equal to the integral. And one thing to notice about this is a divergence, but I think it's worth noting if you're just starting to study calculus and so on. If this formula here only works if the power is not minus 1. If the power happens to be minus 1 for the x, then this is going to be equal to the integral of 1 over x dx. And this is not just x to the minus 1 plus 1 over minus 1 plus 1, because this is of course x to the 0 over 0, and this is undefined. So the answer for this one is actually the natural log of x, which is a function, a function that is called a transcendental function, and it looks something like this. It goes down. This is the y-axis, this is the x-axis, and it goes down asymptotically, never crossing the x-axis, the y-axis, and going to minus infinity here. And here it grows really slowly, uh, on here on the plus infinity direction. It just grows like this. Okay, so that aside, let's go back to the problem here. So the energy is going to be equal to 1 over the capacitance times the integral of q, which is simply q squared over 2. And this is the answer. The energy is equal to q squared 1 over the capacitance times q squared over 2. And so this is it. And I hope you have enjoyed the video. So thank you very much for watching.